So today we're going to talk about lattice energy, what it is, and how we determine it using the Born-Haber cycle. First off, let's define lattice energy. Lattice energy is defined as the energy required to separate 1 mole of solid ionic compound into its gaseous ions. Take magnesium chloride, for example. In the solid lattice of magnesium chloride, when we break apart the lattice, the solid will break into its constituent gas ions, magnesium 2+ and chlorine-, and there will be 1 magnesium 2+ ion for every 2 chlorine- ions. However, the problem we have with lattice energy is that it cannot be measured directly, and it's incredibly difficult to determine experimentally. So, instead we use something called the Born-Haber cycle, which follows principles from Hess's law to indirectly calculate the lattice energy. Recall that Hess's law states that for state functions like enthalpy changes, the overall change of a process is equal to the sum of the changes of its individual steps. If you need a refresher on Hess's law, check out the last section in Chapter 6 in Professor Halpin's notes. The Born-Haber cycle consists of 5 steps, where each step is correlated with a chemical equation and enthalpy change, or delta H. As an example, let's determine the lattice energy for a magnesium chloride solid. Since lattice energy is defined as the energy required to separate 1 mole of solid ionic compound into gaseous ions, this means that we want the enthalpy change for the chemical equation magnesium 2+ gas plus 2 chlorine- gas goes to magnesium chloride solid. First, here's an overview of the steps. Step 1, atomize the metal. Step 2, atomize the nonmetal. Step 3, ionize the metal atoms. Step 4, add electrons to the nonmetal atoms. And step 5, allow the ions to combine to form the solid lattice. Let's talk about each one more in depth now. Starting with step 1, we will atomize the metal. This involves taking magnesium in its standard state, magnesium solid, and transforming it into magnesium gas. The change in enthalpy, delta H1, is equivalent to the heat of formation for 1 mole of magnesium gas. In step 2, we will atomize the nonmetal. This involves taking chlorine in its standard form, diatomic chlorine gas, and splitting it into 2 separate chlorine molecules. The enthalpy change, delta H2, is equivalent to the bond dissociation energy for 1 mole of diatomic chlorine gas, where bond dissociation energy is defined as the standard enthalpy change when 1 mole of gaseous molecules is broken into separate gaseous atoms. In step 3, we want to ionize the metal atom. This involves 2 separate parts, step 3a and 3b. In 3a, we will take the magnesium gas formed in step 1 and remove 1 electron to produce a magnesium plus gas cation and an electron. The enthalpy associated with step 3a, delta H3a, is equivalent to the first ionization energy for magnesium gas, where ionization energy is defined as the minimum amount of energy required to remove an electron from a gaseous atom in its ground state. Next, in step 3b, we will take the magnesium plus gas formed in step 3a and remove another electron to produce a magnesium 2+ gas atom and a second electron. The enthalpy associated with 3b, delta H3b, is equivalent to the second ionization energy for magnesium gas, since we're removing a second electron. Together, the chemical equations for step 3a and step 3b add to form the overall equation for step 3, where magnesium gas forms magnesium 2+ gas and 2 electrons. Based on Hess's law, the enthalpies will work the same way, and delta 3a and delta 3b add to the overall enthalpy of delta H3. In step 4, we want to take the electrons we removed from magnesium in step 3 and add them to the nonmetal atom, chlorine, to form a chlorine anion. The enthalpy, delta H4, is equivalent to the first electron affinity for chlorine gas, where electron affinity is defined as the energy change of a gaseous atom when an electron is accepted. Recall that we removed 2 electrons from magnesium, and since the formula for magnesium chloride includes 2 chlorine atoms, the second electron we took from magnesium will add to a second chlorine atom to form another chlorine anion. This means that we need to multiply both the chemical equation and the change in enthalpy for step 4 by 2. And the overall equation for step 4 is 2 chlorine gas plus 2 electrons goes to 2 chlorine minus gas, and the total change in enthalpy is 2 delta H4. In the last step, we will use the ions that we made in steps 1 through 4 and allow them to combine to form the solid lattice. Here, magnesium 2 plus gas will combine with 2 chlorine minus gas ions to form magnesium chloride solid. Note here that the chemical equation is exactly the reverse of the chemical equation for the lattice energy. Thus, the change in enthalpy corresponding to this step is the negative of the lattice energy, which we'll call delta H5. And allowing many of these ionic interactions between a magnesium 2 plus and 2 chlorine minus ions to occur forms a strong solid lattice. Let's look at all these steps again. If we add the chemical equations for steps 1 through 5, something really interesting happens. Adding the chemical equations together, many molecules appear in both the reactant and product side, so we can cancel those out. Magnesium gas, 2 chlorine gas, magnesium 2 plus gas, 2 chlorine minus gas, and 2 electrons. Now we are left with what we'll call equation 6. Magnesium solid plus diatomic chlorine gas goes to magnesium chloride solid. This chemical equation is equivalent to the standard heat of formation reaction for magnesium chloride solid, since we're taking the constituent atoms, magnesium and chlorine, from their standard states and producing magnesium chloride solid. The enthalpy associated with this is called the standard heat of formation, which we'll call delta H6 for now. Now this is where concepts with Hess's law really come into play. By adding equations 1 through 5 to get equation 6, Hess's law states that we can do the same thing with the enthalpies, meaning that delta H6 equals the enthalpies of 1 through 5 added together. Recall that we cannot measure the lattice energy directly, but the enthalpies for equations 1, 2, 3, 4, and 6 are all measurable. So if we have values for those quantities, we can easily find our missing quantity, which is delta H5. This is again the negative of the lattice energy, and by taking the negative of delta H5, we'll have what we want. Let's look at this more schematically. We have step 1, magnesium solid to magnesium gas, and the corresponding enthalpy. Step 2, diatomic chlorine gas to 2 chlorine gas molecules and delta H2. Step 3, magnesium gas to magnesium plus 1 gas corresponding to delta H3A, then magnesium plus 1 gas to magnesium 2 plus gas corresponding to delta H3B. Step 4, 2 chlorine gas to 2 chlorine minus gas. Recall that we need to multiply this by 2 since we are undergoing 2 moles of reaction, aka taking 2 chlorine gas molecules and adding 1 electron to each to form 2 chlorine minus gas ions. The last step is step 5, allowing these ions, magnesium 2 plus gas and 2 chlorine minus gas, to form magnesium chloride solid. This corresponds to delta H5, which is again the negative of the lattice energy. And all these steps add to step 6, the heat of formation of magnesium chloride solid. So in order to produce magnesium chloride solid, we start with magnesium solid and diatomic chlorine gas. Now there are 2 paths we can take. We can go through steps 1 through 5, or we can simply consider step 6. Either way, Hess's law states that the enthalpy should be equal. So delta H6 equals delta H1, 2, 3, 4, and 5 all added together. And if we put in the numerical values, it should look something like this. Next, we want to rearrange the equation to solve for delta H5, which again is the negative of the lattice energy. And doing all the algebra, we get that delta H5 equals 2,522.1 kilojoules per mole. Since this is the negative of the lattice energy, we simply add a negative sign in front and then we'll have the lattice energy for magnesium chloride solid, which is negative 2,522.1 kilojoules per mole. Hopefully this video helped you learn something about how the Born-Haber cycle is used to determine lattice energy for crystal solids. For more resources like this one, check out the University Learning Center at the Academic Resource Center or at U-Haul.